Okay, so let's talk about the basic thing about the machine learning. So there are really good references so far. So this one, the pattern recognition and machine learning. This is like a probabilistic machine learning. And the Bishop is the undergraduate of the physics. And then while I prepared this lecture, I found another interesting book here. And this is, of course, the Kevin Murphy's probabilistic machine learning. And then this is Ian Goodfellow's deep learning, like a classic of the this machine learning. And then about the physicists, there are also good books, a little bit more practical, the deep learning for the physics research, and it contains so many good literatures, like references. So this is a really good book. And during this school, I think that advanced machine learning will be with the PyTorch, but this is like a KIAS, and then KIAS is a very easy platform so that you can enjoy the very simple network with the KIAS. So this is the book by the KIAS author. So this is a very interesting book. And then my postdoctoral researcher recommended this book. And then recently, also there's a book, there are deep learning and physics. And I thought that this book is very interesting to the particle physicists, not only particle physicists, but in general, the physicists. So there are many good books, of course. But the point is that we can read this book during your weekend, over the weekend, instead of watching the Netflix. You can read these good books, and then you get some kind of insight. And now, for the beginner of this machine learning, there are another Korean books. Actually, this is Japanese book translated into the Korean. This is a really very interesting book, so that you need to write down every detail in the Python itself, not using the library. So the 1, 2, 3, there are 3 books, but one is okay. And while I have this lecture in my university, I found that this is another interesting book. And this is very easy, but it contains many interesting features. So for the Korean student, if you have time, and for the beginner, you can read this kind of the books. Okay, in fact, machine learning, you need to learn machine learning by doing some practices. So for example, like handling the data MNIST or fashion MNIST or cat and dog, the classical, or the IMDb review data set. Playing with this kind of the data, you can get some kind of the hint how you can write down solve the problem using the machine learning architectures. But this is just playground, not enough. So during this lecture, not this lecture, but during the advanced lectures, these lecturers will provide you the homework and some project. And afterward, because you are all professional, you need to learn something by doing the related project. But to do the project near this related with machine learning, this project should be on the boundary of your current knowledge. And what I want to say is that any simple idea or application of machine learning will be welcomed at the first stage of your study. And especially for the particle physicists, this head living ML living review, this is like a kind of the almost complete site for the references of the whole of this machine learning related work in the particle physics. And you can go to this website to check what kind of the related topic are solved using the machine learning. Okay, so I want to say that actually, okay, so don't be shy to apply machine learning, even though this is simple. So things to be covered at this moment here. I'll talk about the deterministic machine learning. So this means that the prediction is determined by the input. So once you construct a neural network, then all kind of these parameters should be get some value to optimize the problem. Then after you optimize the parameters, then it becomes like a black box. So the one income give the same output. So this is called deterministic machine learning. I'll talk about this, and about the probabilistic machine learning will be covered by the advanced lectures, not this lecture. And this lecture is really basic thing. So maybe, I don't know about this spectrum of the audiences. Maybe some of you are really good at machine learning. Some of you are using the Mathematica. Maybe you can find some library even in the Mathematica to do the machine learning, which would be very slow. So the 3 lectures target about this thing, the basic thing. And I talk about the deep neural network and the convolutional neural network and the recurrent neural network. This is really old, like a dinosaur algorithm. But still, it will be interesting to look into the detail about these 3 network structures. Okay, so let's go to the detail. The basic idea of this machine learning. I mean the artificial intelligence, not the machine learning. So I think that all of you heard about this kind of the AI winter and also this expert system. So just like our very arrogant theorist, we are thinking that if we write down every data with every rules, just plug this kind of data and the rule to the computer programming, then this computer can give any answer that you ask. So this is really top-down programming because you write down every detail, every rules. But it is really hard to maintain this kind of the AI structure because if there's some variation, you need to input that variation into your programming. But at the beginning, it worked very well. So there's thousands of the investment about this under this expert system. And afterward, it brought about the AI winter. The second one is the machine learning. So machine learning is nothing but, in my point of view, just give the freedom to the machine, to the program. So you just put the data and answer. This is like a picture of the supervised machine learning. Then by interpreting the data and answers, this program, the algorithm will get some rules. So through the data and studying this kind of instruction, this machine can find a rule which can be generalized. And this kind of the machine learning is realized in the with the old idea of the connectivism. This is a very old idea. The connectivism is like a network mimicking this neuron system. So see, this is how basic it is. So you have the input and there's the weight, and you add this input in terms of the weight. So it's a weighted sum. Then through some kind of activation function. So if this signal is beyond some threshold, then it gives the reaction or ignore. So this is really concept of the perceptron. It's very simple. This simple structure of the neural net. The reason that this perceptron works very well because at the time we don't have the good computer. We have just a wired computer here, just like here, and this kind of perceptron can be realized by this variable resistance. So if there's some signal from the photonic cell, then it gives some response, and this electric response gives this control this variable resistance, so they give the weight. Then this weighted sum and some response, and it figure out what kind of the signal it would be. And at the time of this perceptron, it worked very well. And it was easy to program because there's no hidden structure. So this perceptron is just actually linear programming. So what is linear programming? Linear programming is you can decide the boundary of the two, for example, for the two classification. Okay, so you're not distinguish between this cross and circle using some kind of the plane or line with this kind of linear thing. So this is basically the supervised training. So you give the data and you give the answer. Then this through the training, this algorithm try to optimize this weight to get the answer correctly. So as I said, this algorithm is very easy to realize using the old computer like this. So there are lots of investment, of course. Okay, so let's continue. So this H is activation function. The activation function is a sine function. And this is weight and this is bias. The meaning of the weight and bias is nothing but this to make the plane. So if we put the B equal to W0 and start from the X, then X0 equal 1, then this W dot X equal 0 determine this line or plane. Then this point is the X of this point satisfy this is more than 0, and this part is less than 0. So you need to decide this weight to have that to give the correct assignment of these two categories. Because this is so simple, we can assign very simple algorithm to do this classification. So let me see it in detail. Okay, so at the beginning, because I don't know anything, the computer doesn't know anything, they just put the arbitrary weight. So this is arbitrary weight and a plane determined by the initial weight. Then from here, there are 3 points which violate the condition. Then there are 3 errors, right? So out of 3 errors, the computer chooses arbitrarily 1. For example, if the computer chooses D8, and then the algorithm try to move the plane so that to give the correct assignment for this one. Afterward, now we have the 2 wrong assignment. So out of 2, randomly choose the D1 and try to give the correct assignment to the D1 so that it moves the weight so that it can decide correct boundary for D1. The leftover D3, then do the same thing, like here. Then after this kind of iteration, this perceptron algorithm get the correct boundary between the 2 classification. So this is the algorithm for this perceptron. So this T is the label, the answer. Actually, I didn't explain here the label T. So here T. So this is a true label. So for example, T1 should be minus because it is cross, right? And so, and this is the calculation or expected value coming from the algorithm, from this calculation, W dot X. So this algorithm have this updating the weight to this value. There are the original value plus alpha. We call this is a learning rate, and label minus expectation and X. For example, if the X is belongs to the correct assignment, then because X and belong to the correct assignment, the label and the expectation are the same. Like for example, for this one, plus 1, for this one, minus 1. So this could be 0. This becomes 0, so there's no update. If this Xn is not belong to the correct assignment, so that this is maybe if it belongs to the wrong assignment, then if we calculate this, then this sign of this is Yn. Then because they are different, 1 is plus, 1 minus, 1 is minus, 1 plus. So the total of this one is negative. Then for the wrong assignment, this is negative, so that we need to correct. Actually, the computer needs to correct this value to the larger value. So if computer update W to the W prime, then using this update, if they calculate this value, then through some kind of algebra, then this new updated value case would be larger than the old one. So that after this iteration, this value approach to the right assignment become bigger and bigger. And this algorithm, if we do some kind of the mathematics, then you'll see that this this algorithm will converge, and it will be give the stable boundary, a stable decision. So that actually this is like homework for the student in my class. Anyway, so this is very simple algorithm for the perceptron. It is no magic, just updating, keep updating. So, okay, in the previous perceptron algorithm, this algorithm is based on the one-by-one sampling. You choose the wrong assignment and calculate this and update this and so on. Now, if we use the modern terminology called batch to update, then we add all of this value for whole xi in the sample. As I said, if xi belongs to the correct category, then because they are same, would be 0. If xi belongs to the does not belong to the correct category, or if this belongs to the wrong category, because I have a minus here, it is positive. So that this value will be positive if it have some wrong assignment. Then the algorithm needs to minimize this value. Now in the modern terminology, we call this as cost. And how we can minimize this value? We can minimize this cost using the gradient descent method. So here, the update one is the weight. Update weight is here. So minus alpha gradient of cost value. The alpha is the learning rate. And alpha is a fixed one. Just you can choose positive value arbitrarily. Yes. We call this is a kind of hyperparameter. It's not decided by the computer, it's decided by you. Some kind of input. Then to minimize the cost function, give the same algorithm just like the before. Looks very same except their summation. Now we learned that this old algorithm called perceptron can be realized with the modern language, minimizing the cost function. Okay, so let's talk about this minimization. We call it gradient descent method. This is very simple. I think that everybody here may know about this. Okay, some arbitrary function here. This is like a local minimum. And I choose the weight to this point. Then the cost function value of the cost function is larger than the minimum case. But gradient here is negative. I need to update this weight to the right position, right? Which means that minus of the gradient. If the computer randomly chooses WP, but it is actually at the position of the this local minimum, then at the time the minimum the gradient 0, so there's no update. Just stay here. In this case, if the computer chooses the larger weight, then calculate the gradient. The gradient is positive, but it needs to move to the left. So take the minus sign. So this is in the case of the one dimension, you can do the same thing with the arbitrary n dimension, right? Using the gradient, which is belong to the calculus 2 in the high school days. So as you see, this gradient decides the direction that you need to move. If the gradient directed here, then computer needs to go that direction, the opposite direction. But then, how much they will need to move? Computer doesn't know. You can decide through the this learning rate. But all of you that know that actually to get the minimization in a very good precise way, you may need to the second derivative, not only the first derivative, but second derivative in the computer point of view, it will be very expensive to calculate the second derivative. So in the computer, in the thinking of the computer-wise, that you need to minimize the cost to using the computer. That's the reason that even though you can do the better than this gradient descent way using this different derivative twice instead of just one, but because if you require twice of the derivative, then the computational cost will be doubled. So that the modern computer machine learning language, they just use the gradient descent to minimize the computational cost. Okay, so I think that I cover everything about the machine learning. Yes. Yeah, so this kind of the derivative doesn't know global, it just know the local. Okay, so in this gradient descent method, they just go to the local minimum. They don't know about global minimum, right? So it brings about this local minimum problem if we just using the gradient descent method. Because computer doesn't know about the minimum around that point. They doesn't know about whether this is global or not, right? So it brings some problem. Yes. I'll talk about this later. Yes. Yes. Okay, so now we learned about the basic algorithm about the machine learning. You define the cost function, and then you need to minimize the cost function. Actually, computer need to minimize the cost function by adjusting weight. In the case of the perceptron, this weight is nothing but the normal vector of the hyperplane. After all, computer decided this is a good linearly separable case. Also, it looks very nice. You have very sharp. I think in my case, maybe this looks better than this because it looks really nice, super nice, very sharp. But the problem is that about the generalization. Okay, in this case, with the training and a test to different assignment or data, they don't have any problem, so it's fine. But for example, if this computer get this boundary during the training for the linearly separable hyperplane, then if I do the another test set, then maybe there are some violation like here. So if the computer define this hyperplane of separation very close to this data, then it will fail the generalization problem. It will bring about this overfitting issue. This is a basic idea of overfitting. And these old people know about how to solve this problem. So during this minimization problem, they require some margin. So, for example, okay, when computer decide this hyperplane, okay, there's some margin space between this hyperplane, so that inside this there should be no point. If I have a good big enough margin, then I will not have any overfitting problem, right? This is so-called support vector machine. So in one slide, this is all about this perceptron, the support vector machine. Okay, so, but this is very basic after you learn about the calculus, multivariable calculus in your young days. Then this is a hyperplane, then defined by w dot x for 0. And if there's a point here, the distance between the hyperplane and this would be this function yx or w dot x divided by w. And this is distance here for the point to this hyperplane. And then if this x belongs to the correct assignment, for example, for the positive case is a zero or circle, or negative case is a cross. In the proper assignment, then or if all data is belong to the correct assignment, then the label times this value would be zero, more than zero, because plus plus or minus minus. Then for the distance, I can just make this into this one, removing this absolute sign here. Then okay. Then by this scaling the weight to some kappa parameter without changing the distance, then I can make this distance between the two hyperplane as 2 over the length of the weight vector. And then this is a margin, like a margin here. Then okay, so I need to computer needs to have the maximize this margin, which means that along the for this data, then maximum margin would be up to here, right? If this one, the maximum margin would be here, very small. So that they need to find some hyperplane to maximize the margin. Maximize this margin is the minimize of this one, of course, with the constraint of this. This means that all of the data should belong to the correct assignment, right? Here, rather than 1. Then in your days, all the days of the mechanics, like a second year of your university days, then you need to minimize this under this constraint here. Then what is this? It's nothing but utilizing the Lagrangian multiplier, right? Here. So you have, this, you need to minimize this. And here, you need to maximize this on top of the minimization. But one is the minimization, one is maximization. So you take the minus sign here. Then maximization, this means the minimization of this. So overall, you minimize whole this function, right? With this alpha I larger than 0. This is Lagrangian multiplier. Then if you do some Lagrangian multiplier, then during your break time, then you'll get the answer for the support vector machine. Very easy. See? The machine learning for the physicist, it's just a piece of cake. I'm sorry, maybe not. But you know everything. So actually, I don't need to do this lecture because you know everything. Okay, now the pole of the perceptron. To bring about the post-winter, AI winter. I told you that the perceptron is linear programming. It can separate points using the hyperplane. So if there are this assignment, then I cannot do any separation using the straight line, right? It is not possible. Because of this, the perceptron is broken. So that the government of the United States hold the investment because of this issue. But actually, this is nothing. There's no problem because, I can do some transformation from this. If I have, for example, this function, then I can map this point into another point where, one of the these two blue go to the same position anyway. Anyway, so after using this transformation, I can have a straight line to determine this separation. So actually, this problem of this problem actually means nothing, doesn't mean anything, because I have a simple solution. The issue is that because this kind of thing, then you need to do the minimization with hidden layer. this is this transformation, like we can say this is a hidden layer to transform this data space into another data space. Then from here, I can do this support vector machine, but I need to minimize twice through the one more step. It caused some computational problem in the early days, because in early days, the computer was very simple, just that.
So does this mean that we rely on the specific algorithm to find this hidden function?
Oh, no. Okay, so then I need to talk about the kernel method. Yes. But, okay, so there are some kernel we can apply and check whether this makes linearly separable or not, okay? But don't worry. Not only the kernel method, there's a beautiful way to do that. For the kernel method, if we find really good kernel, the problem will be very easy, okay? But to do that, I need to check with another kernel. Well, there's some algorithm, already complicated, but there are a more simple way, like embedding the data into higher dimension. Actually, this is nothing. It's called Cobalt theorem in the 1965. Any complex pattern classification problem, if we test this into the higher dimension with nonlinear function, arbitrary some function, some set of the polynomial would be fine, then you can linearly separate. So to find this one, okay, I can have this one, but in the theorem of this one, there are a bunch of some polynomial basis function. So if I just write down whole possible polynomial up to dimension n, dimension here 2, 3, for example, then or 4 or 5, then any of complicated distribution can be decreased into the simple linear separation. Also, because now you know about this Cobalt theorem, you can Google it. You can find his paper in the 1965, which is very simple. So, theoretical point of view, this nonlinearity doesn't mean anything. We can solve this problem just cast into the higher dimension. Not only that, as you learned, there are theorem called universal approximation theorem. Okay. Okay, this is some kind of modified version. So for phi, a non-constant, bounded, and monotonic increasing function in a compact domain, like in the 2 dimension here, here the 1 dimension, there's some function, continuous function defined here. Actually, this is a x. I have this homework for this one for you. Then for this function, the blue line, we can approximate this f, small f, in terms of this summation with some kind of basis. And this is the nonlinear function, and this is the just a linear algebra. So there are just some dimension m and value a and the weight and the bias. For arbitrary precision, we can always find. This is a universal approximation theorem. In that paper, he proved this with, I think, with a Lillo function, maybe. And this, I can find in some blog, saying that, for example, this function, there are this 6 segment, 6 function, then this approximation like a red line, the composed of this, and is very closely approximate to the original function. Okay, this is theorem. And it means that with this Cobalt theorem and with this universal approximation theorem, we learn that higher dimension is always better, always good. Make problem very simple. Make the whole complicated problem data structure into the linearly separable space, right? And for the universal approximation theorem, in terms of the modern neural network, in this case, for example, actually this is -5. So x is -5, And okay, so I can write down this in terms of this neural network and this weight here. For example, because here there's no bias here, so the bias go to 0. And here, after this, this is activated with the ReLU. I forgot the ReLU here. Activated with the ReLU, then they are minus, so that this one, the weight is minus. And this plus, 3 is plus. Then, okay, so you can find this using your mathematical, but I can find this kind of the approximation using the neural network. So I define it should be positive, not a minus. Right. Positive. I think this is a typo. Then define this original function and this approximation, here the g, and try to minimize for the data that I have. For example, 20 data or 100 data. If I try to minimize this cost function through the neural network, then I can find the function which can approximate this original function. And anyway, so here I need to define the distance to think about the closeness of between the function. This is one thing. The other thing that during this training process, the training parameter that computer needs to decide is the 19, because here 2 by 6 and 1 by 6. Oh? Yeah. Anyway, maybe 7. Oh, yeah, 7. So, yes. So, so computer through this mindless neural network algorithm, then they can find the optimized weight function to minimize the distance between the original function and your answer. Okay, so we learned that the higher dimension is always better, but actually it is not. The basic idea of this universal operator theorem is that we just need one hidden layer, right? For the power of explicitity. But if you have the large enough dimension M, any complicated one, you just need one hidden layer if we have large enough space, data space. But this higher dimension gives you some problem. According to the, okay, for the Wikipedia, this is the dimension 0, dimension 1, dimension 2, dimension 3. I draw this hypercube. Actually, I don't know how I can draw this hypercube in dimension 4, but this is drawn in the Wikipedia. But this side is length 1. Now, then we cast a random point inside this hypercube. Then we'll measure the distance between the two arbitrary points inside hypercube. You can do this test in your Mathematica or you're using the Python. Then if I cast the arbitrary point into one dimension, then measure the distance, then this is a histogram of the distance and the mean value 0.33. If I cast any arbitrary 2 point and measure the distance and draw the histogram, looks like that. The mean distance is 0.52 and 0.66 and 0.77. Okay, of course, by our intuition, we know that if we increase the dimension, then this distance inside hypercube will become larger and large. And it means that the larger distance make the computer larger dimension, and the larger distance make the computer become more hard to find the correlation between the 2 points. So this is the so-called cost of the dimensionality. Okay, in the previous slide, we saw that, of course, this is by instance, the distance between the arbitrary 2 points increased with dimension m. Not only that, okay, for example, the density law for the given number of the data n becomes sparse as dimension increase, because the density is behave like a number of 1 over m, this is dimension. So that density becomes sparse. And if we have 1 point, and if we draw the this sphere with radius 1, and take the share of the sphere from where this distance is epsilon. Then I just checked the population of the volume fraction for the whole sphere over this one, this shell. This is the volume of the shell, because radius is 1, and this is the whole volume of the sphere with radius 1. Then if you calculate this one, is 1 minus epsilon m, m is dimension. And for example, for the dimension 20 dimension space, if I take this epsilon as 0.05, 5%, then this radial 5% shell contains more than 60% of the population. So they are dense here and sparse here. And then, okay, so the computer wants to think this is one point, and computer try to find some kind of correlation between the nearby neighbors, right? But they cannot find. It will be very sparse because many of the population go to this shell. So if we increase the dimension, then computer cannot find correlation very easily. That is the main problem of this cost of the dimensionality. Not only that, if we increase the dimension, then configuration in the lattice will increase exponentially. In any case, if you increase the dimension, you need to pay the price, right? So increasing the dimension does not looks like solve your problem, but actually it brings about some another problem. So we need to think, okay, using the universal operator theorem or the cover theorem, I can just increase the dimension. But then if I increase the dimension, then I have the problem of the cost of dimensionality. What can I do? Okay, instead of increase the dimension in the one specific hidden layer, I can make the neural network deeper and deeper, right? Like this. For example, there are six nodes in one hidden layer, or I have the two hidden layers with each hidden layer contain the 3 nodes. This connectivity means the number of the trainable parameter, which means the number of the power of the expressibility, like here, right? Then for that case, the power of the number of the expressibility, I mean the number of the trainable parameter is 19. But in that case, the number of the trainable parameter is 22. So you have more degree of freedom compared to this, right? Even though you have the same 6 nodes. Okay, so far so good. Now, if I have, for example, take the activation or nonlinear function as this cubic, the square function, then all of this looks like this square. But for this 2-layer, hidden layer, this guy will have the polynomial up to the x to the 4, right? More powerful compared to this. So now we learn that, okay, so all the days, because you don't have the good algorithm, good backpropagation algorithm, you need to rely on the one single hidden layer. Then you have the problem of dimensionality. Now, if we have some kind of algorithm which can calculate this derivative in a deeper layer, then you don't need to go into this high dimensional problem, but you can use deeper neural network, which give you more freedom. So now the issue is that how we can train the deep neural network. As you know, the answer is we know the answer, right? Due to the Hinton, the answer is this backpropagation. So the backpropagation is systematic, and the issue is the backpropagation is inexpensive, very cheap. This is the main point. Very cheap to calculate this derivative using the computational graph and the chain rule. You will learn about this quantum machine learning in this week. But in the quantum machine learning, quantum computer cannot use backpropagation algorithm. You will learn why not. anyway. So that in the variational quantum algorithm, to calculate the derivative of the weight function require huge computing, unlike the classical computer. So can you have some coffee? Or we can continue? I start from 9:30 to 10:30. Okay, so I think that many of you require caffeine. So we'll have the 10 minutes break to continue this problem. Yeah. Okay, so let's start. Yeah. Okay, anyway, so in the previous lecture, I missed one node here. So previously it was 5, now it has 6. Okay, that was my type error. Okay, so now we ask how we can train the deeper neural network. This is the one simple example of the computational graph. This is some operator. I have two input, x and y, with plus operator, and I have z. So z is x plus y, and through some function, the L is the function of z. So this direction is forwarding direction. So forward propagation. Now let's go back to this direction to get the derivative of L with respect to the x, or derivative of the L with respect to the y. It's simple just using the chain rule. So derivative of L is x is a derivative of the L to the g and g to the x. Similarly, here L to the y and L to the g times g to the y. So the g is x plus y, so that if I derivative the g to the x or g to the y, it gives the 1. Then the derivative L with respect to the x is this one. So this is the contribution from the former step, and this is a new contribution, in this case, 1. So here, the derivative of the Lx is this one. Similarly here. So this is a new contribution in this plus operator. Similarly, if I have the multiplication, for example, I do the same thing. But because g is x times y, if I derivative g to the x, it will be y, and g to the y is given x. So for this x operator, the new contribution is nothing but a swap for the two input, right? So if I have the x input and y input, then from the back propagation, the new contribution is this one, and for this case, it will be here. You can do the very similar thing for the exponential operator or derivative or division operator or minus operator, anything, just like this. And this is like a simple building block for the propagation and back propagation. Now, let's have this example. G to the gamma times W1, X1 plus W2, X2. Here the X1, X2 is data, and now omega1, omega2, well, W1, W2 is the trainable parameter. To have this final answer, then I can write down this computational graph. For example, here, X1 omega 1 times give the X1 omega 1, and X2 omega 2 times give the omega 2 X2. And if I add these two, then I have this omega 1 X1 plus omega 2 X2, and another contribution gamma multiplied by this multiplication node, then I have the final answer. This is a propagation, right? Now, our goal is to find the d omega 1. This is just definition of the some loss function, derivative of the loss function with respect to the omega 1. Similarly, I define the d omega 2 as the L over the omega 2 and the d gammas. So I have the optimization process L with these variables. with back propagation. So first, if there's a loss, some function L as a function of the G, then this gives the dL over dG. Now this one, because this is a multiplication, as before, the new contribution is nothing but the swap between this and this. So here, this one from this one, and this one is nothing but this guy, right? Based on this. And then from here, I can read off the derivative of the loss function with respect to gamma will be this. It's a very systematic way. Then getting further, from here to here, then because this is adding, so that back propagation gives the additional one, just one. Additional constant parameter is one here and one here. So, and then I have this process of this back propagation. Now the final would be this node, this one. Then with the same, this swapping, so that new contribution here would be omega 1, new contribution here, this times x1. And similarly, also here, derivative of the L with respect to omega 2 is this one times this one. So using this very systematic computational graph and back propagation, we have all of this derivative, very systematics. And then you realize that to have this back propagation, you need memory this intermediate process, right, to get the final answer. Now we know how to utilize the back propagation to have this derivative. Now I need to talk about the vanishing gradient problem. So in the modern machine learning, the ordinary neural network is very deep if we have the good enough data. So this is the input layer, and there are a bunch of the hidden layer and this final output layer. Now let's talk about this activation function. If I have the activation function, if I have a sigmoid as my activation function for each node, activation function is nothing but do the nonlinear transformation from this input, right? So this nonlinearity is given by this activation function here, the sigmoid. Now, if my weight was here, then the derivative here or derivative here is very flat, right? And if this kind of this flat region is very very large compared to the very sharp region. So there are many good chances to have all of this weight belong to either this region, flat region, or that flat region. So if I doing this back propagation, if this activation is flat and there's a flat, so that zero, almost zero, then the final one over here, all it becomes zero, right? There's no update. So this is a so-called vanishing gradient problem. It's arising from this kind of the flat region. Actually, there's a reason that people love this sigmoid function. So, but okay, I think that I don't know about the history, but for the old person, we should use the sigmoid function, and we need to find some way to get rid of this vanishing gradient problem. But young people like you, they can ask, what the heck of this sigmoid? I don't care sigmoid. I can replace sigmoid with some special another function if I can have some good performance, get rid of this vanishing gradient problem. For example, like this ReLU function. Okay, this is a rectified linear unit. So this is a non-linear because it's real non-linear. But this is a zero region, but this is non-zero. This is a derivative is always one, right? So if my weight is belong here, then derivative is always given one. So they don't have any this vanishing gradient problem as long as they live here. But if they live here, then it means that they shut off this network. So in many problems, this ReLU doesn't mean give the good performance out of this vanishing gradient problem. But in some cases, if we don't like shutting off by this flat region, then you slightly modify this ReLU function with some arbitrary, some slight with some slide. The lesson here, I don't care the history of this sigmoid, an interpretation of the sigmoid in terms of some activation or some probabilistic point of view. I can just cook up some simple function which works very well. I think that this is one of the core of the machine learning. I do some exercise, some experiment. If you give some good answer, then I can write a paper, right? That's it. So it's called really heuristic problem. It works very well empirically. But there are some problems so that people modify a little bit. So anyway, this is the vanishing gradient problem, can be solved by this ReLU function. Then another problem is it's really opposite to the vanishing gradient problem, which is called exploding gradient problem. For example, I wanted to fit this dot with polynomial. This is m is a degree of this polynomial. We can call this as a degree of the freedom. If m equals 0, this is nothing but constant. If m equals 1, linear. M equals 3, this one. M equals 9, this is super crazy. I can fit anything, right? Okay, so then the coefficient here is, we can call this as a weight that computer need to figure it out. If I draw this weight in terms of this fitting, as you see, the weight for the m equals 9, this case, is huge. Ordinary, huge. But I like this because it fits the training data, training data. But actually, the original function coming from original data coming from here, green curve, and this is through some smearing effect. Then this great fitting doesn't mean anything, right? It's just overfit. I need to get rid of this kind of situation. Need to go back this one. How can I do that? If I observe here, usually the overfitting result give the result in the huge weight. Then if I restrict the weight, length of the magnitude of the weight, then I can evade this kind of situation. And this is like overfitting. For the data, training data, it works very well. But for the another testing, another random sample, really big gap.
I have one question.
Yes.
I guess, I mean, when you try to fit in the number of free parameters of your test function is maybe should not be more than the number of data points, right? Roughly. So
yes, so there is one good observation. Usually, yes, usually if we have not enough data compared to your degree of freedom, then mostly you will get this kind of overfitting issue. This is a good observation. Thank you. So, but here, okay, so I can increase the number of the data to get rid of this overfitting, or through this observation, I can restrict the magnitude of the weight like this. So this is again Lagrangian multiplier. So this is the magnitude of the weight in the hidden layer L, L's hidden layer. And for the all of this, some of this weight of the hidden weight. And here, okay, this is ordinary loss function, and I have this additional this constraint. Then with this regularizor, if I want to minimize the whole thing, I need to minimize this one. Also, I need to minimize that one, right? So by adding this kind of regularization term, I can restrict the magnitude of the weight. So this for the physicist is just nothing but the Lagrangian multiplier. So if I want to have the more constraint on this weight, then I need to increase the weight lambda, right? So decide the lambda is like another hyperparameter in your case.
The more the training, the larger the weight will be. The more the training will be. If I train more, then it's overfit, right?
No, if I have more data to train, you will have less overfitting. So compared to your network size, if you have good enough data, then you don't have this kind of overfitting problem. If we have the less data compared to your depth of your degree of freedom of your network, then you fall into this kind of the overfitting problem.
The weight will be larger. If there is overfitting, then the weight will be larger.
Yeah.
That's why the weight will be.
So here the reason that I consider because usually through the observation, if I have this crazy overfitting, then this weight should be large to have this really crazy behavior, right? So if I restrict this large value of the weight, then computer cannot have this kind of crazy behavior. Then they cannot fit. Then they go into this scenario where the less degree of freedom. Okay, so I explained this overfitting problem, and then I think that you asked a question about the local minimum problem. Okay, so this machine learning always look into some local behavior because this is coming from the first order derivative. First order derivative is always really very local, very local. So at the beginning, when you train your network, you just computer just choose one random point for the weight to do because they need to calculate something, the loss function, the cost function. So if the weight starts from here, then through this gradient descent mechanism, it falls into this one. If I stuck here, then it's stuck here, right? It cannot get rid of this one. But the global minimum here, but because of this gradient method, the computer algorithm stuck here, which I don't want. So that was one issue long time ago. But nowadays, I think I heard that computer people doesn't care about this local minimum problem. Because this, this kind of this potential or this cost function is made of the trained data, right? If I have a really super good at the global minimum out of this trained data, it means another overfitting because it's super fit with this potential coming from the trained data, right? So usually the concept of this, I heard that this nowadays modern concept, maybe people don't care this local minimum problem anymore, but at the old days, people care. Then people need to develop some kind of the algorithm to get rid of this local minimum problem. There are many algorithms, and then there are also people use the Adam optimizer nowadays. But to explain the Adam optimizer, I need to explain two more concepts. So instead of explain the Adam optimizer, I explain the very simple algorithm called momentum, one of the dinosaur algorithm, the classic. It is nothing, just like this. So, so ordinary gradient descent method just get the update coming from only from here. But now, if I need some algorithm to get rid of this local minimum, even though this becomes 0, then there's another kickoff coming from this velocity, so-called velocity. So this is a derivative, like a step, previous step divided by the current step minus the previous step. So this is a difference in the step mean that kind of velocity. So I update the not the position but the velocity. So here the current velocity is coming from the previous velocity minus this one. This is a gradient descent. So for example, in the previous gradient descent method, in the case beta is 0, then if you put the beta is 0, then it recover the gradient descent method. Now for this momentum algorithm, which have the kind of kickoff, then I should have non-zero beta. And in the paper of this momentum algorithm, through some experiment, they write down that beta equals 0.9 give the good performance. So ordinary like a KIAS or maybe PyTorch, the default value for the beta in the momentum algorithm would be 0.9. But this is a hyperparameter you need to change for yourself by looking to performance. This is a one-dimensional version, and this is a two-dimensional version or n-dimensional version. So this gradient method, and this is the momentum method. So using this one, I can get rid of this local minimum here, go to this one. But then because this is still there, so that maybe there are some cases where this is going to like that and that, if you have the huge beta. So that also you need to control the beta. So this is people developed some adaptive method to control the beta. But anyway, so basic idea of the get rid of the local minimum have some another kick off. It's very simple. So now we know that how we can train this deep neural network. Okay, let's design a deep neural network. One is the width of the layer or the depth of the layer. So there are two hyperparameters in terms of the number of the neural network, number of the hidden layer, or the number of the node in each layer. This is kind of the parameter that you just choose for yourself and test it with this experiment. Anyway, okay, so there's one other concept. Okay, this wide large width or wide less give the high dimensional performance, make it easier to separate. If you narrow down the width, it imports a neural network to extract some meaningful information. So it called information bottleneck theorem. It's nothing but here, if you increase the number of the layer, number of the node, give the freedom to the computer. If you decrease this node, it imports this computer to extract some meaningful thing. So this kind of information bottleneck is utilized for the autoencoder, for the data compression. Anyway, so you have for example, two hyperparameter, number of the layer, hidden layer, or depth of or the number of the node. So usually we can do through this grid scanning. I have this length of the hidden depth, and maybe each layer have the 1 or 2 or 3. Anyway, so it's like equally scanning. But usually this is not good because maybe one of the hyperparameter is not so much sensitive to give the good performance. So usually you can do some kind of random search and get them. Yeah. So this is one way to get to find out the good hyperparameters through some experiment. So anyway, this is the structure of the neural network. Then in the paper of this efficient net, which I found through a book that I recommended, not recommended, actually I'm selling to the Korean student. Maybe not, because I didn't write down. Okay, some experiment. So, okay, for the baseline neural network, actually this is a CNN. But anyway, so there are ways that you can make this network is more reachable. One is the wide node for each layer, or very deep neural network, or make this picture more high resolution, more fine data, or higher resolution and deeper and wider. Everybody can guess that the answer to get the good performance would be combining all of three, right? This is like a computational cost, and this is accuracy. Then if start from the baseline, if you increase the width, then but basically it becomes flat. And similarly, if we only increase the depth, suddenly now it's getting flat, saturated, or the more higher resolution, similarly saturated. So this is then baseline, then this is a higher resolution, and this is a deeper resolution, deeper network, and this is the higher resolution and deeper, and in terms of that means this width of this neural net for the given layer. So as you see, if I utilize make it deeper and wider and higher resolution, if we have good enough data, it gives you better performance. This is everybody can guess. So I don't know why this become a paper. It is cited a book, and I think that this is maybe very easy to make you understand. But anyway, so if we want to increase the size of the neural network, then we need to increase the depth and width and resolution altogether to get a better performance. But if we make this network is getting deeper and wider and complex, then you need to pay the price, which is the data, number of the data. So as Byung-hun mentioned, if you have small data compared to the size of a neural network, overfitting will occur. Okay, so for the given neural network, if the size of data is smaller, then for the training compared to the test, we have this gap. So to avoid this kind of overfitting, you need to increase the data. But increased data is really expensive especially in terms of the supervised learning. Actually, when you have this supervised learning, you need to have a label, right? The answer. But who give the answer? The computer? No, human. Human prepare the data set. So this is a labor fee. So now all of this salary go up. So nobody with a small salary, nobody can do this. Nobody will do this kind of the huge labor for the labeling the data. That's the reason to give the birth to the semi-supervised learning. Actually, semi-supervised learning is nothing but the old idea, which is the data augmentation. Okay, anyway, so there are many cases where we don't have enough good enough data. For example, very expensive to label the data, or rare samples. Like a data-driven method, but you have the real small controlled data. Then how we can make the data larger? Okay, for example, this kind of image, like this is 6, the handwritten 6. You can rotate, you can make some noise here, you can stretch some modification. Then to human, they are all just the same. You just rotate and make it thicker and some noise there. But for the computer, this is new. So this is all the idea of the data augmentation. But if you do the data augmentation, you can improve this overfitting problem. Okay, so in short, learning process. You have data here. You have N data. You feed into the neural net. You get the prediction. This neural net is you can think this is one black box as a function of this weight. And you need to get the weight to minimize the cost function or maximize the probability. So we take the sample in the data set, and each sample is from the independent and identical distribution. This is very important. When you're sampling a data from the data set, if this sampling depends on your process, then you cannot train this data through your ordinary neural network. But as long as this collecting data, sampling is they are independent of each other, then you can train. So this is very important and very simple and very, very, very understandable, but very important concept we call IID. Anyway, in the IID, if sampling and training and the computer for the given weight, it gives you how the data, the probability of the maker data. Then, because this is IID, we can multiply each data, each probability for the given data, right? Because they're independent. We can call this is a likelihood. So to reduce the cost function, it means that it is to maximize this likelihood. But this multiplication, maximize the multiplication is not easy. So we take the logarithm and take the minus. If we take the minus and logarithm, it goes to this one, right? And so change into the sum. Now, we define this as a cost function, and this is summation. So we can find the weight to minimize this cost function, right? Okay, so let's take one example. Okay, for example, for the supervised machine learning, one typical example is regression. In the data here, the computer needs to find some relation between these two data. And if for each, this is expectation, and for the some error, and this is observation label. So okay, for the if this is simply this distribution coming from the Gaussian for the regression, then this each probability is nothing but Gaussian here. Then if we put this probability in terms of the Gaussian, put back into this log and summation, and after some 2 or 3 lines of the calculation, it poured into this mean squared error. Right? This is MSE. So usually when you train the data for the cost function, if your problem is belong to this kind of the regression, then you use this MSE for the cost function. Right? Now, for the classification, okay. Now, if we have some kind of the probability that show up in some specific choice, then for this classification, like this binary classification, this is probability is coming from the Bernoulli distribution. So this is a probability to have this event xi, and the t is 1 or 0. If one happens, the other is like this, because this is binary. Here the binary. So now this probability coming from the this Bernoulli distribution, and this is a probability to have the this classification, one specific classification. If you have the one selecting data, then if I take this into this logarithm, after some calculation, it gives, and if I do this what? It should be not the same, but go to the modification a little bit to the mean, then it gives the cross entropy. So usually for the case of the classification, for this binary classification, you encourage to use this kind of the binary cross entropy. Similarly, okay, but okay, now I said that for the case of this cost function, for this classification, we need to use the cross entropy. Now, what happened to this activation function? By the way, for the case of the this regression, you take the linear activation at the output, it'll be fine. But for this classification, okay, this is Bayes theorem. So if you have the observed x, then what happens to the y? Then this is like that. Then this probability x belongs to the C1. Can you have the x and this probability give the, you need to estimate what is the probability for the x belong to the some class C1 coming from D, then you can calculate through this Bayes theorem. Then if you define A to the like this and do some mathematics, then you can take this, you can convert this into this form, which is nothing but the sigmoid. So for the this binary classification, for the activation, we use sigmoid, right? That's the reason that people like to use sigmoid for kind of this probability distribution, because like this. And now, finally, the multiplication. For the case of the multiplication, because each of these independent, you have this multiplication. For the each probability, with the class K, we have the now, for this example, you have the K equals 3. And then the all possibility for the class 1 to K should be 1, because one can belong to, one need to belong to one of this K out of K. And the label also, one is one label should be 1, and the other should be 0. So anyway, if you take this this probability of the categorical distribution to here, do some mathematics, it gives this entropy. And similarly, for the multi-class case, then do the similar thing using the Bayes theorem and have this substitution, then use some mathematics, then we go to this softmax for the activation. So for each node, you have this softmax function for the activation. So for the case of the multi-class, then you get to know the activation for the final output layer as softmax, and then you have this entropy for the host function. Now let's talk about a little bit about the information and entropy. Actually, so what is information? Information means something new. If I keep talking about this kind of very mundane and very stupid talk about this ABC of neural network, maybe some of you who know the machine learning very well, it's very boring, right? Because it doesn't contain something new. So like here. So for example, there's some message, we have a sun or some cloud, it's nothing. But if you have some Godzilla in the Seoul station, it means something, okay? So some rare event means big information. So to quantify this information in terms of something new, okay, rare probability provide a good information, which is a huge information, and we can add in the individual information. For example, for the event X probability, for event Y probability, if two of them are independent, then X and Y, the probability come with X and Y is nothing but this. And for the information, you need to adding up. Then one simple way to satisfy this and this, you can define information like this. Because of log here, you can have this multiplication into the summation. And this is log function, minus log function. 2 means the digit, binary digit, for this bit configuration. So anyway, for the high information, high probability, this h goes 0, and for the very rare, this h goes to infinite. So this definition satisfies this and this. So we can use this as the amount of the information. Now let's define the entropy in terms of information. So entropy is defined as the expectation of the information. So this is expectation of the information. You do this weight summation of the information in terms of the probability. Then because information is minus log p, so this is we call entropy of the information. With this information, if the probability distribution is something like that, then this case h is 1.77. If the probability distribution looks like that, then in that case, the entropy is 3.09. So because this is really disordered compared to this, right? If a very sharp probability distribution, that it always gives this kind of the cases, which mean nothing. But if it's really wide, then it's very disordered. So it gives the higher information, higher entropy. Now, okay, let's define the cross entropy for the dissimilarity between the two probability. Let me have the probability Px and probability Qx. And then if you have this define cross entropy is the expectation of this log Q, the information of the Q with respect to this average with respect to the P, like this. This is an asymmetric definition. So anyway, if we define this, then for the cross entropy that we have these binary cases, like here. Now, when the T1 is 1, so that out of two, the case there's when the label T1 is 1, then if you plug T1 is 1, then this expression goes to here. Then if you draw this one, it's like that. Now, what is this? So if the prediction of the X1, your prediction is this one, then in the case, this is low, right? Because they are same, so that it should give the low cost. And if its expectation is really different from the actual value, then this is the case when the U is 0. This gives a huge differences. So similarly, when T1 equals 0. So in terms of this entropy, the cross entropy is just have a distance between the two probability, right? Compared to the your expectation from the machine learning neural network to the actual probability. Okay, so this is an example that TensorFlow playground. If I click here, then it go to the this very, maybe some of you know this. And this is like many cases. So for example, I want to do this classification between this and that using the neural network. So because this is the two-dimensional data, I have two input, x1, x2, x-coordinate, y-coordinate. And my hidden layer, if I have the one hidden layer with the 4 node, and then output is we can have the 1 or 2, because for the binary classification, we have 1, but just for the classification, we have 2. And if I do this, because this is very simple, then it tries to find the boundary, right? So this is expectation boundary. It goes very well, right? And the cost will become very saturated to the low value. But if I increase this hidden layer, then increase this, then I can have much faster, right? And very well, looks like very circle. But not only that, okay, so here are just two coordinates, x and y. Now, but you know that, wow, wait a second, this is like a radial distance. So that for the feature, I can have the x1 square and y square, x2 square, right? Then if we have this one, it gives really super converging, nice separation. Okay, so basically, we don't know, we don't need to worry about the feature of the data. We just put into the neural network, then it gives good separation. But if we have some kind of domain knowledge, then you can put this into your input, it makes really super nice separation. So even though the machine learning can do something better, something good, but if you know some physics very well, you can have some feature engineering, which is actually against to the modern machine learning. But I want to insist that your domain knowledge on the physics make neural net converge super fast and super clean and very explainability. So your physics will be welcome for this kind of the separation with some neural network. See, it's super beautiful, right? Compared to this stupid one, right? Yes.
So in the input, we know that x1 scale is nothing other than the scale of the x1 value.
Yes.
But in neural network, does it know that exactly x1 scale is the certain input variable? It's just the input variable of the scale of the first input variable.
Eventually they'll know because they'll see but so look at this.
Probably we know the correlation, but probably we doesn't know that the certain variable is the scale of the first.
Yeah, at the beginning he doesn't know. Yes. Yeah, because you don't have the direct connection between this node, right? So if you know, then go through this kind of thing, back and forth. Then they can know through the, but yeah, it takes some time and much data to figure out, but not exact, not the perfect. That's the issue because this all of this is numerics. Yes. Yes.
Here, the distance.
Hmm?
You have put the distance measured here as a physics input, and you get a better.
Yes.
You have an optimum number of physics information that you can put in.
I don't know. So I think that, I don't know, maybe the other experts know the better answer, but in my point of view, people you do some experiment, nobody knows.
guess I can ask.
Oh, yeah.
So, I mean, here, so here in the input, I mean,
Yes.
as a human, we know that there is a 100% correlation between first and the third vector.
Yes.
100%
Yes.
correlation.
Yes.
But here in this neural network,
Yes.
I mean, he knows here there are quite strong correlation, but not 100%, unless he get an equation.
Yeah, they have approximation, but not exact.
Right. So that
Yes.
means that the output of this answer
Yes.
will be biased somehow in systematic. Since probably it takes probably like 95% correlation between first and the third,
Yes.
not 100%.
But here, actually, if this is more efficient, then it will shut off this and this, and focus on this. So the contribution coming is determined by the weight of each connection. What happened to my? Okay, so there are some toy, and I provide this PDF, but you can click this one. When you can search for TensorFlow playground, then this is very simple. And they also say that you cannot break the system, so just to play around. Now, let's do some MNIST example. So this is a very standard example, like a set A, when I give a lecture to the student. Okay, so this is data, like handwritten, and for example, 5, and some deep neural network and the classification. Then using the deep neural network, it gives the probability whether this belongs to some category, right? So if I adding all of this probability, it should be 1. And for this case, it gives the 5, 0.8, 4 is 0.04. So that mostly 5. There's one concern for this deep neural network, because for the image, if I have this pixel size, pixelized, then this here number is nothing but the density of the pixel. And if I have this into the pixel, I have this. And for the case of the MNIST, you have the 28 by 28 pixels. So total, this input is 784. And you have the input of 784, and the output is a 10 classification, 0 to 9. Using the softmax and the cross entropy. When you do this to the training, one way that you can train that you put the every data, train data to make the cost function. So put every data that you have into the neural data into the neural network, adding up all of this data, the cost, adding the all cost function from the data, and propagation, and calculate cost function, backpropagation, doing this job again to search for the local global minimum. But because the computer requires the whole memory, huge memory for this whole data, it has some memory issue. So in practice, if you play with this neural network, the GPU with huge memory costs a lot. You cannot train this huge data in one shot. The other way is mini batch learning. So out of this huge sample, I take the randomly a few, like in this case 5. And take the 5 and propagation, cost function, backpropagation, parameter update, apply to the another 5, and to this one, and another 5. This kind of iteration using some kind of mini batch, it really gives a good answer. And it based on this statistics theory. Or you can just do the update one by one data by one data, right? This is very crazy. A huge iteration, but if you write down this in terms of the C++ or Fortran, it'll be fine. If you write down this stochastic method one by one with Python, then you'll be crazy again, right? So Python is not good at this iteration for the one by one loop, one by one. So anyway, this is totally stochastic. You can do that. And let's compare for the gradient descent with the whole data, single shot to the iteration, very smooth manifold of data, and get trace of this. So mini batch, moderate sampling to this iteration, well stabilized. The crazy one by one, very randomly. But anyway, it gives the answer eventually. So the problem now, okay, I understand. Okay, we can use the mini batch to calculate this cost function, update the neural network. But what would be good number for the mini batch? This is another hyperparameter that you can try. So example, for some cases, I can use 100 as my mini batch, or maybe 100 is not good enough. Maybe 100, then maybe not that, maybe a little bit more unstable. So I can increase like 100 more. If I increase this number of the mini batch size, this data size for the each mini batch is 100 times more, then using those simple statistics, this deviation is coming from the this square root n. So I just increase just 1 over 10, right? Decrease 1 over 10. Uncertainty decrease 1 over 10. So not so big deal. So if we increase this mini batch, number of the mini batch, then you can stabilize and you can have reduced your deviation, but not so much. It goes to the 1 over square root n. But anyway, deciding the number of the mini batch is one hyperparameter you can decide. And people talk about one epoch. One epoch means that when you use up all of the data that you have statistically. So for example, if my size of the mini batch is 100 and my data have the 10,000, then if I do iteration using the 100 mini batch 1,000, then statistically I use up the whole my training data. This is one epoch. So now you got to know that some kind of jargon of the machine learning, right? You know what is the cost function, what is the backpropagation, and what is the mini batch, what is the epoch, you know everything. Left over is that now, okay, so I need to tune the hyperparameter, but as I said, when you do the supervised machine learning, the data is very expensive. So in most of your actual cases, you are limited with the number of the data. But I need to do hyperparameter tuning independent of my training data. So to do this kind of hyperparameter tuning economically, then people prepare this K-point validation. So for example, I split the data into 3 partitions. Then out of 3, this first to third is my validation, and this left 2 is training. So this one through this one, for the given hyperparameter, I have this score. And to do this as my training, and this part is my validation, I get the score, and so on. Then the total validation for the given hyperparameter is the average of this. And even though there are some, then validation is kind of independent, statistically independent, so that I may be safe to have the good statistical approach for the validation of hyperparameters using this K-point validation. So there are something that you need to think about when you do this hyperparameter tuning. Okay, so the example is administered with the DNN. It should be given to you. Now, for the 10 minutes, let's talk about this CNN. Okay, let's go back to this DNN with the MNIST. For example, for the 8, this 28 by 28, this one. Then for the DNN, to input this 2-dimensional array into deep neural network, I need to flatten. So that my input node is the 784, which is 28 times 28. Okay, it's okay. And the input layer, number of the node for the input layer is 784, so what? And I can just propagate and get the reverse and so on. I can get trained. But, wait a second. Anyway, so this is okay, so this is like a deep neural network. So for the hidden node, this one is like a linear transformation. We call it affine transformation. Then the activation as a ReLU. Then another hidden layer, affine again, and ReLU, affine again, ReLU. Then final answer is softmax. Then for the 8, give this high priority And for the 1, give this one, and for the 7, should give this one. So it works because this image is kind of simple. But the issue here is that the fully connected deep neural network actually cannot easily figure out the neighboring pixel. For example, I have this one, and next to this one, I have another dense pixel. But if I flatten this into this flattened layer, then position this guy would be 240 position, and position of this guy would be 267, because it have the 28 distance. So even though in the image wise it's very close, but if we flatten this one, it get the long distance, right? So flattening spoil this closeness of this each pixel. That's one of the problem. The other problem is that because, for example, if I have the input 784, and then next hidden layer is 5, then in that case, the number of the trainable parameter would be kind of 3,000. For example, around 4,000. It's huge for the one step. If we have the huge complexity, then you need to worry about this kind of the overfitting issue again. So instead of this, people develop this is also another dinosaur algorithm called convolutional neural network. It's a convolutional neural network is nothing but it's just filtering. So in the Photoshop, when you do the filter, for this filter, then you can identify and the edge, or if you have this filter, then you can blur this image and so on. So depending on the filter, it can change the image. If you have this filter, then you can sharpen the edge. If you have this, then you can average this. So if you apply a filter to the image, it can get some information out of the picture. So that is the basic idea of the convolutional neural network. So this is a process that doing the convolutional neural network. You have the image, like here 5 by 5, and a filter, and this is like a elemental-wise product. And if you have this convolution, then it go to this and multiply the pixel by pixel, element-wise, give the 4, then you move on the next one, give another 3, and so on. Like this. So this convolution is very simple, but it is powerful. And this is like a convolution again. Now, but for this moving the same filter here, right? Then you need to decide how much this filter move along this image. It called this as stride, another hyperparameter. You can move this filter one by one, or here with a stride 1. Then if your input image is 7 by 7, and if your filter is 3 by 3, then result in the convolutional image would be 5 by 5. If we move the filter like 2 and 2, like this, then the output result would be 3 by 3. So that even though you have the same size of the filter, if you change the stride, then it gives the different convoluted image. So this is another hyperparameter. Now, when people talk about the pooling, I'm sorry, not pooling, when padding, then if you choose some stride out of mindlessly, this case, for example, if you move 3, then you end up here, you cannot cover this one. To resolve this issue, people enlarge this picture with adding 0 pixel here. Then with this increased size of the image, you can use the stride 3 to do this convolution. So this is some jargon that people talk about when they talk about this convolutional neural network. Now, for the case of the color image, okay, so you have the RGB, for example, 3 color, or track, E-car, H-car, 3 color. or X-ray, gravitational wave, neutrino image, whatever. 3 channels, for example. Then you do the filtering, this filter. And in the convolutional neural network, after you do this convolution, each channel, this one is this, and this one is this. After you do the convolute, you're adding up. So the number of the channel for the filter should be same as the number of the channel of the input image. But after you convolute, this algorithm is adding up. So actually, I'm wondering whether maybe there's some case that this convolution, this adding up channel maybe gives some bad result. Maybe some, for example, if we have some another image, which is like a red, green, blue, but another ghost image, which is really different, right? Does not have the correlation for this RGB, like another ghost which does not have the RGB. Then if we're adding up, then it destroys this kind of the ghost image, right? So there are some cases that CNN doesn't work anyway. And after filtering, this is some mathematics. Then for the size of the H and wide, and this is padding and the size of the filter, height and the width. Then to the filtering conversion, you can have the, for example, like this. For example, 32 by 32 image, and the padding is 0, and the filter size 5 by 5. Then result one is the 28 by 28. So mathematics, just to decide the image after convolution. So as I said, for the multiple channel, the result one is the adding up these channels. So the generic convolution structure is something like that. You have the input image, have some channel, multiple channel C, and this is the size of the height and width. Then for the convolution, you should have the same channel for the filter. The result one have only one channel, but this one. Because you're adding up, this algorithm adding up all channels, contribution of all channels. But I want to have more channel here, right? I have those three, like RGB, but I want to have some kind of more flexibility, more degree of freedom. Then to do that, I have, I'm sorry for the Korean, I have the multiple set. Then if I have the Fn set over this, then after this convolution, I have the Fn channel, right? By doing this kind of multiple set of filter, I can increase this complexity. I'm sorry for another Korean. I copied my previous lecture here, but in the morning, I deleted all Korean except some cases, right? So here, okay, this filter contains the weight, right? And after you convolute this image with the filter, multiple filters, then this is bias. So if you have the Fn set of the filter, then you should have the Fn bias. If we have only one set with FH, FW, FC, then you will have only one number, right? But if you have N set, Fn set, then you have Fn bias. After all, you have this. So this is the basic idea of this convolutional neural network. Now you know how to do convolute. Now let's talk about the virtue of the CNN. Okay, unlike this DNN, which flattening. Because, yeah. So by the way, so actually also I don't like this flattening. For example, if we have the pore vector, right? But when you do this low pore vector particle into the neural network, you do the flattening. We have EX, energy, and the momentum X, momentum Y, momentum G in the separate. This pore vector does not move separately, right? This pore vector should be processed all together. But if you're flattening this pore vector to input the neural network, you make this energy and PX, PY, PG separately. Then it really makes stupid. So I was worried. I worried about that. Then, like me, people worried about that. So people invented like this Lorentz neural network. So anyway, so what I wanted to say, when you apply some neural network in your physics domain, there is something that you need to worry about. If you worry about something to make this neural network more make sense, then you can develop your one nice neural network for which is very good for your specific domain. Anyway, so let's talk about the CNN. So because through the convolution, it have a good understanding in the neighboring pixel. Not only that, because this filter is moving around, and then weight is sharing through this stride, then the number of the weight in the convolution will be reduced. So this we call it parameter sharing. Okay, let's think about this. So for example, for the fully connected DNN, for the this 784 input to the 5, maybe this is not, this is right. For this process, I have almost 4,000 learnable parameter from here to here, but in the same 5 by 5 output, then if I do this 24 by 24 filter, then the size of filter is 567, and then you have one bias. So in total, the trainable parameter is only 577, which is significantly smaller than this. So this parameter sharing is really good to make the conversion more fast with a small number of data. So CNN works very well for the image. Another one is that if you train this 5, if this 5 image inside your training data set, but if you test your trained neural network, DNN, with this test image, DNN doesn't know whether this is 5 or not. Because for our point of view, this is really same to shifting, but as I told in the data augmentation, it's really different image for the DNN. But for the CNN, because they are this striding, usually the CNN is strong against this translation. And now talk about the pooling. Okay, what is the pooling? Okay, in the CNN structure, I talk about this convolution. This is nothing but the converting with a kernel. Then this nonlinear activation, like a ReLU. After you make the nonlinear, then you do the pooling. What is the pooling? Pooling is nothing but the pooling a process to reduce the size of data. It's same as kernel, but it does not contain any new trainable parameter. For example, for the 3 by 3, if I have the apply 2 by 2 max pooling, then from here, then I take the maximum only, then 4. And to the pooling here, the maximum is 5. And pooling here, maximum is 7, and pooling here is maximum 8. So with stride 1 through the pooling process without any additional trainable parameter, I have this output. So pooling does not contain any new trainable parameter. So there are two typical pooling. One is max pooling, the other is average pooling. Then why you do the pooling? Okay, I want to reduce some data size. So what? Not only that, this pooling process makes CNN become strong against some change of the local structure. For this kind of the image, if I have this max pooling, I have this one. Now I shift this into one pixel, but with this 3 by 3 pooling, 4 by 4. Anyway, 4 by 4, then I have the same output, right? So pooling make this kind of local shift does not change the structure, does not change the output. So this is one of my typical example. Actually, I worry about some kind of hot pixel in the which is already different from the distance. For example, I have two hot pixels. This one is a large distance. This is some smaller distance. A little bit change, but in the ordinary DNN, they are really different. But because pooling have this strong against some local change, after you do the pooling, this is the same. Yes. So I'm done for the convolution. So this is where thing that if you go deeper and deeper, is look at the really deep meaning of the structure. This is a user say, this is coming from the Yang Fellow book. And okay, so okay, let's look at this, talk about more about this sparse interaction, which is nothing but filtering. So we have this. If you have this filter size 3, mean that in the one dimension, the input and the output, this one have the 3 sides. So this 3 give a pixel, give the 1, this one. Now if you have the input and this one, second one first hidden layer, second hidden layer with the 3 sides of filtering, then this guy look into this, but this guy look into that, and this look into that, this look into that. It means that eventually this guy know about something for this very wide. So to do this kind of filtering and convolution process, then as you get deeper and deeper, it look into the more wide range of the information. Get the more correlation for the wide range. So for the 2 dimension, if you have the 3x3 filter, then this one, if the 3x3 filter goes to in this one, then if I have the 3x3 filter, because this is 3x3, it gives just 1 dot, 1 pixel. And this contains this 9x9 information. So it's abstracting, right? It's the abstract. So this is really good for this CNN. And I said, if the shifting give the same answer, right? Because CNN is strong against this translation. And the size resizing, it is fine. This is VNet on one example of the CNN. But rotation a little bit different. If you do the rotating a little bit and for some more degree, give the 1. So rotation is some problem for the CNN. That's the reason that people develop another algorithm to resolve this issue. And stretching, it'll be fine. For some cases, it collapses into 2. And this, and thicker, and noise. Noise is okay because you have the pooling, right? Pooling make this CNN algorithm is stronger for the noise insertion. So we talk about everything about the pooling. Now, one simple thing. Now, okay, you have the big data. Then I cannot resist myself to make this network is big and deeper. I want to do this because I have the 800 GPU, which is really expensive. I can make it deeper and deeper. I can process through my GPU. But if you have the limited data, or you have data and if you go deeper and deeper, there are some problem, again, the vanishing rate problem, so that for the deep layer doesn't work very well because of the vanishing gradient problem. Again, there are some processes, some algorithms who can dilute this vanishing rate problem, as I said. But one simple thing that I can have another skip layer identity. So even though they had a problem to go to the vanishing rate problem, they have this shortcut which contain the information, so that it kind of the shortcut was some identity path, resolve this vanishing rate problem. So then I can make a deeper for some cases and a good performance. See. So this making this simple skip, or not skip, actually not skip, because identity some another path, adding another degree of freedom, another path in this neural net, CNN. It is nothing, just adding up. For the deep neural network, then I have better performance. So my last message here that neural network is not magic. You need to suffering through this neural machine, these learning processes, and I have no idea. Let's do something simple, which make really nice. So if we want to do the neural network more like a professional, you need to lots of exercise, like know-how. So this is the end of my second lecture. Okay, thank you.
Park?
Okay.
So student can ask a question, very serious question, even during the lecture. Okay.
Of course, yeah. So the last part is last part of the dinosaur algorithm is RNN. RNA is a recurrent neural network, in short. I did. Yeah, I did. Okay, so okay, in short, RNN is the this to study about this time series or some kind of series of the data with this simple network. So this is like a zip version of this RNN, and this is a closed loop. And if I unfold this loop into the this, then this xt is the vector of the some data, and it's in the time series, for example, x0, x1, x2, xt. All of this can be a vector or array or some high-dimensional object. Then this is like some neural network, and input here and calculate some kind of the hidden information, and it go into this and combine into the new input and give another hidden information, and the same thing is branched out here and so on. And this module, as you see, it contains the same weight for in each time component. So it also shares the runnable parameter along with this time series. So this network can be utilized for the many applications. One is the image caption. So here, one image and with this, and it can identify the object. Then talk about this what is object here and here. So for example, if the cat and dog and some human children run with bicycle, then it object tagging and give some story. And the other one is like a forecast, for example, stock marketing, telling about the stock forecast or some weather forecast, whatever. So based on the previous data, it can tell about the future output. And one is the translation and the many-to-many model. And this is another many-to-many. So each structure, each network provides a hidden information, but you can utilize each hidden information to the output, or just one, or some part of this. So this is the basic idea of this recurrent neural network. Let's go into more detail. So here, the basic activation function for this RNN is a tangent hyperbolic. And this, if we look into this here, then for example here, then it have the previous hidden information combined with the new information. So this is the previous information and combine the new information. Here, for the new information, you have the weight and also another weight for this hidden information, and adding up and the bias, and this is a tangent hyperbolic activation function make a nonlinear. So it give this, and this one go to the another next network, and same information can be utilized for the output for the stage. And so here, then we can have this back propagation, and you have this output hidden layer and go to the back. You can just trace back, and that is a tangent hyperbolic, and you can have the computational graph, get each of these derivative. It's very simple. Actually very simple. And as I said, if we have some kind of many-to-many model, then for each output from the hidden layer information, you can take into this output through some kind of activation, some processes. So this is like a many-to-many model. For example, this is a little bit more detail for the structure of RNN. So here, this is many-to-many, and I focus on only two structures, the one RNN and the other RNN structure. And set the hidden information and the input and adding up for this one and this activated here, and this is the output. And you can calculate the loss function. And for the another next time step, you can have this hidden to the here and branch out and go to the another information, and similarly here, and next hidden information and activate and output, calculate this another loss function. And for the total loss function, you can add this stage loss function plus that stage loss function as total. So a little bit tricky here. Now, this is, you can find this derivative of the total loss function based on the, with respect to this weight in here. And the loss function is coming from the, this L1. So you have this loss function can be derivative with this. And also, you can have the loss function here L2. Anyway, so this H and this H coming from the DH, blue coming from the this loss function. And this DH and DH1 also coming from the this loss function. So that in this derivative, the total DH1 is adding this contribution and that contribution, right? It's color code. And here, you have only DH2 here. And also, this is the weight of the DH. This WH is the weight multiplied by this hidden information. But one concern here, as you see, this DH is coming from the this and this, because we repeat this weight and here. So as you see, this DH is have the blue coming from the this and red coming from here. So this is the total contribution for the DH output. And similarly, DX, you can calculate it very similarly. So here. So this tracing this derivative coming from the backpropagation is not trivial. A little bit looking into the detail of this neural network. And similarly for the magnitude 1 model, because here, even though we have the hidden information, we don't have the output. We only have the output here from the final stage. Like you try to estimate the future based on the previous time step, time history. And in that case, even though you have this, but you don't have the loss function here, you only have the loss in the second stage. So the DH is only 1. And WH, we have 2 contributions. So based on this kind of the backpropagation, you can, as I told in the first lecture, it is very systematic to trace back to this derivative of each trainable parameters. The concern here is the problem of this gradient vanishing or gradient explosion. Because this vanilla RNN, the RNN share this weight function, weight matrices for the H, for the hidden node or for the input node for the every time step. So for each here and here, you multiply, this network multiply the same matrices for the WH and also WX. Now, if you go back to this through this backpropagation, then because in each case, the activation function for the nonlinearity, they use the tangent hyperbolic. Then if you derivative, the tangent hyperbolic is 1 minus tangent hyperbolic square. So you add this one. And for the each have, you have the contribution so that this, because this is multiplication, when you go to this then, from here to here, this guy comes to here for the additional multiplication for the back, in the process of the backpropagation, as I told in the first lecture. So this multiplied here and this multiplied here. So every step, the same matrix is multiplied. So in the final stage, this whole same multiplication from the repetition of the same matrices is here. If this component of the WH is larger than 1, then through this backpropagation, because you have the multiplication of the more than 1, the value, then for the time backward step, this will diverge. It is this weight, this gradient explosion, or if this maximum of this WH component is smaller than 1, then going back to this time step, then it will decrease to 0. Then this is the case of this gradient vanishing. And this is the case of the gradient explosion. So the reason that we keep this same weight on every step, because you share this same weight to have the whole history. Then you have this problem. So the vanilla RNN was developed to trace back to the time series, but it is not good enough because of this problem. Of course, you can solve this problem in many ways. One way is the cutting off. It's called this gradient clipping. So if this gradient is larger than some value threshold, then you cut it off into this factor. Through this factor, you just rescale down. Then without the gradient clipping, then this gradient is going larger and larger, so it's really going like crazy. But if you have this threshold cutting off, then it can modulate this behavior. So if you have the gradient large in this point, without the gradient clipping, without gradient clipping, then it next step goes to here. But if you cut off this into here, then you can trace it back to this surface of the clip. So this gradient clipping can be utilized in RNN, not only RNN, in some additional, some usual this gradient descent method. So it's a very universal way to cut off this large contribution. We can utilize this in the RNN. The other way to do this is to add new paths, just like this CNN case. So this is a vanilla RNN, as we have. But now, on top of this vanilla RNN, you add another path here. And after you add another path, giving another path means giving more freedom to this neural network. And then to control this another path through the neural network, you provide some kind of gate, some shut-off switch here and here, here, and there's 3 gate as the sigmoid, which is 0 to 1. So if this sigmoid go to 1, then you accept all information. If sigmoid go to 0, then it block this stream. So this kind of the neural network we call the long short-term memory. I'm so poor on the Korean. I changed everything to except that. So here, this is original RNN here. And you add this new path, we call this long-term memory or cell state. And this is a short-term memory on contrast, and we call it hidden state, as I said. And here you have additional switch here, here, and here. This is a switch to accepting this input, so you can call this is an input gate. And I'm sorry, here, because you take it here. And this is here the forget gate, because you have this one, and whether you have accept this previous information or not. Forget gate, and this one go to here also input gate, and this one go to here, go to this one, so output gate. So you have output gate if the sigmoid is like 1, you accept the all information, and then you have this multiplication that go to this tangent hyperbolic activation for the long term and here. So this long term memory can get the update from the new input and old input and so on. Okay, so actually that's it. It looks very complicated, but it is nothing except you add more degree of freedom. So as I said, each gate have this sigmoid, which is 0 to 1. And if the sigmoid is 1, then you accept all information. If the sigmoid is 0, you block all information. I think that, so now here we have this long-term memory, and this is like a matrix form of this each gate contribution. And here you have this weight for each block, but this sharing over the whole time series. And here, this the updating the cell state is coming from this and this, right? And the short term here is from here. So that's it. And because of that, you'll see that this one, just like the case of the CNN, this modulate this repeating multiplication, because in every step of this, it have the pocket gate, which is the different in every time step. So this path modulate this gradient problem because it multiplied different values, not the same value. So this is the magic, which is nothing, but this is actually magic to resolve the problem of the RNN. Okay, so I think this is the end. So up to here, what I want to say from my point of view, the neural network is not magic. And then all of you have already know everything, nearly everything. You know the statistical physics. Actually, I didn't talk about this another contribution coming from this more than backpropagation, like simulated annealing. But I didn't talk about that. But the statistical physics and this Lagrangian multiplier from the mechanics, and some kind of the people talking about this information geometry, like Riemannian, whatever. So this you all learn about from the relativity, and also some kind of the enumeration group in the neural network. We learn about from the quantum field theory. Maybe all of this topic will be covered by the other expert. So you know everything except the practices. So one thing that if we have some problem, just give a freedom to the neural network. That's it, and give more data. Then, as you learn in the first lecture, because of this higher dimension, it resolves everything. But there's one thing, as I keep talking about this, there's one famous theorem called no free lunch. Actually, all of you had a free lunch. Actually, there's no free lunch. Come on. What is it? So any elevated performance over one class of the problem is offset by performance over the another class of the problem. So there's no universal neural network which can solve every problem in the best way. It means that we don't know before we do some experiment using this graphic card. So, and according to the Kevin Murphy, this is like a author of the one book that I was selling in the first lecture. We need to develop many different types of model. So it's welcome. You are welcome to develop your one model. Nobody blame you. And the model performance depends on your problem, your data. So as I said, so there is no magic. However, nice paper advertise a fancy model. We cannot say anything about this performance before we apply this fancy model, because it maybe that fancy model specifically good have the good performance over that example, and we need to further develop our one network so that. By the way, so previously, actually I don't like this machine learning because whenever I try to have some project, I need to go to the computer science people and asking about some good neural network, the fancy neural network to get the idea to apply here. But now I changed my mind because of this no free lunch theorem. Okay, so, okay, this is the price I just said. Okay, so the price is the two homework problem, but actually we didn't provide the problem yet. and a project in this school. And this project is already uploaded in our website, and all of you got email, right? And most importantly, talk to your advisor to have some initiate some machine learning related project. If we don't have any idea, go back to the head reading review, get some references, then you'll have some idea. Don't be shy. Okay, so practices. So some of you may know about Kaggle. Actually, Kaggle is very good to practice your performance over the understanding over the neural network. So not only Kaggle provide this playground for you to develop your knowledge in the machine learning, but also it gives the money. So, if you go to this Kaggle homepage and there are competition, I just type the physics. Then I found that there are ice cube tuning, deep ice, 50,000, but it is closed, sorry. The earthquake prediction closed, and the track ML already closed, and the flavor closed, but not bad money, right? But also there's a HIX competition in the long time ago, like 9 years ago by Atlas, which is another good money. So I think that you got some good playground, because here, if this project is closed, competition closed, they need to announce, the first or second prize network. So you can play with that network, which get the good performance, or you can develop your one network to compete the old one. Not only that, I realized that last week there was an announcement about this nanograph and also ice cube, right? Last Friday, and also this gravitational wave detection. For 2 years ago, they have this competition with this money. So after you learn this advanced neural network by the next speaker, then you can try to get some idea, right? So yeah, I didn't expect that I finish this third lecture very quickly. This is the end. Okay, so before end, I think that yeah, look at this one. Look at this crappy. Oh, I'm sorry. Maybe I need to do this. Okay, give me a second. Wait a second. Maybe this one? No. Okay. Maybe this one? Not this one. I'm sorry. There's so many open window. I don't want to spend my time here for the. Where is the crappy? Not this one. Give me a second. So I have some write-up for the. Oh, I'm sorry, I cannot find it. But I tried to share, and then I lost. Give me 1 second. Yeah. This one? Oh, this one. Okay, so this one. Yes, yes. Okay, let's share this one. Okay, okay. Okay, so this is a really crappy example. You know that when I teach the neural network to the student, I prefer to use the KIAS, because KIAS is very simple for the beginner, and while the PyTorch is a little bit more for the more expert. But because the second lecturer will give this example with PyTorch, I try to implement all of my exercise from written in KIAS into the PyTorch, and I succeeded only this one. This is the one about this universal approximation theorem. So here, okay, yes. So here, this is a function, the cubic function x minus 1, x plus 1. This is the function that I showed in the first lecture when I talk about this universal approximation theorem. And you may remember this is the shape, right? And then I told you that I can utilize the one hidden layer with 6 nodes in the and with the activation function of the ReLU. So here, okay, see how I'm sorry, but how ugly this touch structure. I created this array and need to change into the array into a touch tensor and make the touch tensor as a tensor data set. And then I have the batch, mini batch, with a one mini batch of 1,000, right? Then this data loader is making this mini batch randomly out of data. My data set is like 10,000. And my original data is 10,000, and my mini batch is I hear 1,000. Yes. And then in the code app, you can you can utilize the GPU. So here for the, let me see. Oh, I think, I forgot. Wait a second. There's some, maybe notebook set? Here, in the notebook setting, you can see I have this option. None means the CPU, and GPU, and TPU. But here we use GPU. And the pre-GPU on the collab is T4. And A100 and V100, you need to pay. But T4 is not bad for this simple exercise. And here, this one is that because I utilize the GPU as a T4 in the setting, if I load the information, then it said that it uses CUDA, meaning that it utilizes GPU from the Google Core app. And here, I just said, mini batch size 100, and randomly choose this mini batch out of the total data, and with a random shuffle. Then this is actually after to this, and okay, here you can click this button, or you can shift enter to upload, to execute this command. Anyway, then I write down this neural net, simple neural net. So touch, and then this neural net sequential means this structure. And I checked that most cases, currently Google Core App have the PyTorch already installed. So you don't need to install PyTorch in your Google Core App. You can just run the Google Core PyTorch. So here from the PyTorch, I have this importing this one. And also I have, okay, for this one, this is a linear, and this hidden layer. So from the one, input is 1, because it's a coordinate of the 1 dimension, to the 6 hidden layer, 6 node in a 1 hidden layer, and the activation is ReLU. And from the hidden layer with the 6 node, the output node is 1. And I need to attach this to the device, which makes me crazy. And then I define the loss function here as MSE. So this is the model prediction minus this the answer, QUC value, and get the mean value of this error. Then I define this actual cost function. Then I call the Adam optimizer. Actually, I didn't explain about the Adam optimizer in this lecture, because if I want to explain Adam optimizer, then I need to explain the some adaptive method and so on. But I didn't do that. Anyway, so Adam optimizer is one of the most good, actually best optimizer in nowadays. So by default, you use the Adam optimizer. For the Adam optimizer, you have the three hyper parameters. One is the running rate, the other two, beta gamma is for the controlling the decay of the weight and so on. But by default, they have some assigned value coming from the paper of the Adam optimizer. So I just control this running rate, it's 0.01. And then I have this epoch numbers 1,000, which is crazy. Usually 10,000 epoch is not really huge. And then look at this. And then because here, then I do this iteration. So I repeated the epoch. And then dispatch from this data loader, and this is like a list of the data loader. Then I get this from this data loader, get the train, X train, and the Y. This is a label, and I calculate this cost coming from this neural loss function. Right. And for the loss function, actually it also lead to the propagation and get this loss function. And then I apply this back propagation. So initialized, so 0, and do the back propagation for the cost and optimizer step. So optimizer, you apply the optimizer for the Adam optimizer over there. Then I need to compare the cost coming from this and actually this and for the previous one. So if the current cost is lower than the previous one, I switch my best loss to the current cost, and save this model into using this command. Actually, this kind of the command line you don't need if you use KIAS. So 3 lines is enough. But if you get some experience on the machine learning, then you want to have more freedom. That is one of the reasons that people want to use the PyTorch instead of the KIAS. So anyway, so this is like the structure of this neural net. Then the epoch. I print out every 100 epoch, and this guy give the cost of the iteration. And here, for example, they keep reducing this cost function, but after some step, it is just stabilized. Okay, so it means that actually you don't need to go to this 1,000 epoch. You can stop here. So to stop here, you can write down the simple code to do the early stopping. So early stopping is another skill that I didn't explain that can reduce this overfitting. So anyway, so because I didn't talk about this early stopping in my lecture, so I just keep calculating this epoch to the 1,000. After I calculate this epoch, then the final one is saved here for the best weight that I got through the machine learning that I plot here. So as you see, this yellow line is the original line, and this prediction not so good, right? Because of this huge number of the 1,000 number of epoch, I have this crazy, not good approximation. Why I couldn't have this? Because unlike this universal operation theorem, I only have the one hidden layer with just 6 nodes. So if you want to increase, then you can add here more hidden node. For example, now 6 to 3, then 3 to 6, something like that, or 2, right? And 2 to 1. Then you can add more hidden layer, okay? Then you will get the more better performance, I promise. But I am afraid to run here. If I cannot get the good performance, then I should run away. So you can practice with a very simple example. You can practice this universal problem theorem using the neural network. And this is very simple. And I uploaded this simple code to the our homepage for the beginner. And not only that, I have a bunch of examples which is written in KIAS, like predicting this oscillating function using the RNN or cat and dog with the data augmentation. But written in KIAS, I should translate this KIAS code into the PyTorch. And during the lunch, I learned that maybe ChatGPT can translate my code into the PyTorch. I try in this week. So yeah, so this is the end of my lecture if we don't have any questions. Okay, thank you very much.